Okay, quantum mechanics. First foray into quantum mechanics for a Gen Chem series. We've got this wonderful quote from Niels Bohr. Anyone who is not shocked by quantum mechanics has not understood it. And we'll see some other such similar quotes from other famous minds in the field. So until the beginning of the 20th century, so the 1900s, it was believed that all physical phenomena were deterministic. So if you've ever seen like a video of something that's like about to go wrong, and you're like, it freeze frames and like moments before disaster sort of thing, because you can see like, oh, their elbow's about to bump the glass vase off of the table and then it's going to shatter on the floor. That's deterministic. Once you bump the vase, it's going to fall, it's going to hit the ground, presumably it's going to break. And so this is how all things were believed to be, even at the super, super small level. However, work done at that time at the early parts of the 20th century, they discovered that for subatomic particles, so things that are smaller than atoms, so think protons, neutrons, electrons, the present condition, the present state, does not determine the future condition. So just because you see the trajectory of the ball coming in towards your bat does not mean that it's going to land where you think it does. Just because you see the car careening off the side of the road doesn't mean it's going to actually careen off the side of the road. It might magically right itself and now it's driving perfectly straight. And so that's part of what makes this so key and weird, this whole chapter. So the quantum part of quantum mechanics refers to the absolutely small. So a related way of like how words work. So data refers to a set of pieces of information, a bunch of different pieces of information. One piece of information would be a datum. And so similarly, quantum is one piece of a quantity. So it's like the smallest little bit of something that you can possibly achieve. So it's the absolutely smallest little tiny bit. So we're talking about as small as it goes. And this is the world that electrons and other things live in versus our macroscopic, our big world. So we're talking about really, really small stuff. If you are not observing it, very small particles like electrons can be in two different states at the same time. So electrons can do really weird stuff. I'm not 100% sure how electrons behave myself. I just sort of think of them as like their movement path. They're just teleporting around, which is fun. An unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. So the microscopic, submicroscopic, subatomic world doesn't really make sense to us because we don't live there. Electrons are really small. A single speck of dust, the smallest piece of dust, has more electrons than the number of people that have ever lived on Earth. So you've got many, many times more than billions of electrons just in a single piece of dust. They're way smaller than we can imagine. The electron behavior determines some of how atoms behave, and so that's part of why we're going into learning about how electrons behave. Electrons also, weirdly, behave differently if you observe them. So an observed electron behaves differently from an unobserved electron, which makes it hard to measure them. Because if you go to take a measurement of things that are really small, it changes the way that they behave. And so you have to scientists go through all these hoops to try to design an experiment that lets you secretly observe particles. We're going to observe it, but not directly because that would affect the measurement. So we're going to try to figure out a way that we can indirectly observe the electrons. Just kind of we're going to side eye, just kind of peek over at the electron, because if you observe them directly, it changes things. There's lots of fun videos about Schrodinger's cat. And here we've got some more of our quotes. So this is that Niels Bohr quote that we saw before. Anyone who's not shocked by quantum mechanics, the way that the smallest bits of the world work, has not understood it. Schrodinger, that's the guy with the cat that's in the box that's dead and alive until you open the box, said, "I don't like it, and I'm sorry I ever had anything to do with it." And Albert Einstein's spent a lot of time trying to disprove quantum mechanics. There's also a very good Richard Feynman quote that's not in here. I don't remember what it is off the top of my head. So the quantum mechanical model, we're attempting to explain the way that electrons exist and the way that electrons behave. This will let us do a couple of things. It'll help us explain why some elements are metals and others are nonmetals. It'll help us explain why some elements gain 1 electron when they're forming an anion, like all of our halogens, and why some gain 2 or some gain 3, some lose 1, some lose 3, some lose 2. It'll help us explain some of that. It'll also help us explain some reactivity and some periodic patterns. So there's trends of like atomic size, ionization energy, metallic character that are also kind of explained based on stuff that we learn in quantum mechanics. And we'll see those mapped onto the periodic table when we get to them. For now, though, we're going to start by talking about light. Light is a form of electromagnetic radiation. So the electro and the magnetic parts are referring to 2 different perpendicular waves. So if we think of one of them as going up and down, the other one is going side to side. And they're like overlapped. And this is surprisingly difficult to do. So those 2 things are going on at once. One of them is the electric field, and this is where an electrically charged particle, like an ion, would experience a force. And the other part is the magnetic field, where a magnetized particle would feel a force. All electromagnetic waves, things like light, radio waves, X-rays, gamma rays, move through space at the same constant speed. The speed of light in a vacuum, we're just going to assume that things are in a vacuum, is 3 × 10 to the 8 meters per second, which is 186,000 miles per second. So you maybe heard this fact before, that light is fast enough that it can go around Earth 7 times in 1 second. We unfortunately cannot travel that fast. Okay, so here's a visual of the electromagnetic radiation. So we've got in red the up and down, the electric component. So a charged particle would experience a force from that part. And then we've got the side to side that's sort of coming out of the board, and that's the magnetic component. So electromagnetic because it's got an electric component and it's also got a magnetic component. And the oscillating part just meaning that it's going up and down. So if you've ever seen a sine function on a graphing calculator, it looks something like this. It just repeats up and down as long as you care to look at it. You may also know that light is very fast compared to sound. So the example that we're looking at here is there's a lightning strike and you see the lightning hit, and then depending on how far away it is, it might take a couple of seconds, and then you hear the crash of the thunder. And so there's like different methods that people have for estimating how far away the lightning strike was. You know, oh, I saw the light and then I counted a certain number of seconds and we divide that by a certain number, and that tells us how far away the lightning strike was. A way that we experience this probably more frequently is you hear like a jet racing through the sky and you go and look up at like right where the jet sounds like it's coming from, and then it turns out that it's like half the sky ahead of where the sound is coming from. That's because the light is traveling so much faster than the sound, so there's a big lag between light and sound for us. Some properties of waves. So there's some ways that we can describe waves. The amplitude is the height of the wave, or the intensity of the wave. So we've got a node. Our node is like our baseline for the wave. And from our node to a crest or to a trough is our amplitude. So our amplitude is from where it averages out to 0 for our wave. It's from there to our crest. And a larger amplitude, taller peak, is going to mean more intense light, or a more intense wave that you would experience. So if you think of being at the beach, because that's where we would often see waves, really big waves, you maybe don't want to go out unless you're surfing, and then maybe that's a good reason to go out. Right? Big waves, if you get hit by a really tall wave, it's probably going to knock you down. If you get hit by little tiny waves, it's probably just going to be kind of nice, and it might splash up your leg a little bit. So just like waves at the beach, taller waves mean more energy. That also applies to our light. Taller waves mean more energy. Short waves means less energy. We've also got wavelength, and this has the symbol lambda, the Greek letter lambda. And wavelength is measuring the distance from one peak to the next peak, or between a trough and the next trough. Basically just like the distance between the waves. So distance between waves. And we've got some examples of different wavelengths and different amplitudes. So on the left we've got different wavelengths, and it turns out that wavelength determines color, or is at least related to color. So for a long wavelength, like we see up here, this is our example A, we've got red light. For our example B here, we've got a shorter wavelength, and so we've got yellow light. For C, it's even shorter, and this is our, I think it's blue light. And the different amplitudes determine different levels of brightness. So a dim light is going to have a small amplitude. We're using dim and bright here just compared to the other one. So again, tall waves, lots of energy or really bright light. Short waves, low energy, dim light. Another term that we've got for waves is frequency. And frequency has this symbol, which is the Greek letter, the lowercase nu. And I'll usually write it with this big left tail, or sometimes not quite that big, but with a left tail so that you can distinguish it from V. And the frequency is the number of waves in a given period of time. We usually describe this as the number of waves per second. So waves per unit time, and our preferred unit of time is seconds. So hertz is typically our value for frequency, and a hertz is just an inverse second. So 1 over seconds, or per second. This is the same hertz that's like for our power supply. We've got like 120, no, it's not 120, it's 60 hertz. Like some lights, like LED lights, if you look at them through your like video on your phone, it like flickers if it's like an LED light, and that's because it's turning on and off like 60 times a second. We don't see it because our eyes just average it out, but your camera picks it up because it's also taking pictures every 1 in 60 seconds or something. Incandescent lights don't do that because they don't turn off between the waves of the peak. Frequency also shows up in like music, so different frequencies correspond to different sounds, but that's for sound waves, and we're talking about light waves. The total energy of the light, of the electromagnetic radiation, is proportional to the amplitude of the waves and the frequency. So larger the amplitude, the more force it has. So big waves carry more energy. And many waves carry more energy compared to fewer waves. So going back to the beach analogy, if you can imagine laying on the beach and it's a nice sunny day out and you just would like to chill and read a book and maybe get a little bit of sunshine. A peaceful day, in my mind, is waves crashing maybe one a second, one every other second. You just hear them crashing. Versus a chaotic day, a high energy day, there's constant waves crashing, crash, 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 crash. I don't have audio files for that. But that's what I think of when I'm thinking of frequency. Lots of waves in the same amount of time versus not very many waves in the same amount of time. Lots of waves is going to be chaotic, high energy. Not very many waves is going to be calm, relaxing, low energy. And there's a relationship between wavelength and frequency. For waves traveling at the same speed, which works for light, because light waves are traveling at the same speed, the shorter the wavelength, the more frequently they pass through. So I'm going to draw some really bad waves. Okay, I've drawn worse waves. So if we can imagine, let me continue this. Oh, it's so bad. If we can imagine these two waves both traveling to the right at the same speed, the top one, because the waves are closer together, we're going to get more waves passing through. The bottom one, the waves are longer, and so we're going to get fewer waves passing through. So we've got a relationship between our frequency, nu, and wavelength, lambda. Since the speed of light is constant, if we know the wavelength, we can find their frequency. So they're related, and they're inversely related. So really long waves, if wavelength is really big, then the frequency is going to be low, not many waves passing through. If they're really short waves, then we're going to get a lot of waves passing through, high frequency waves. And we can also do math with this equation. Okay, going back to the wavelength, very briefly mention that wavelength and color are related. So you may know that white light, like we get from the sun or some light sources, is a mixture of all the colors of visible light. And visible light is on a spectrum. And that spectrum is the same spectrum that's the rainbow, and oftentimes abbreviated Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And so if you pass light through a prism or like the right angle of glass, that can diffract the light out into all of its different wavelengths. And since it's got all the wavelengths, we get a continuous spectrum. So we don't have any like missing parts. So it's a continuous spectrum because all the colors are in the white light. And then also worth pointing out, when an object absorbs some of the wavelengths of white light and reflects others, it appears to have color to it. So the observed color is predominantly the colors that are reflected. So like in this example image that looks like it's from the early 2000s, a red sweater reflects red light. Most plants, if they're alive, are green. What color light do plants reflect? Green. A blue hoodie reflects blue light. A white and red or pink shirt reflects white, red, pink. So the color that you see is the color that's being reflected. The other colors are being absorbed. So you're just seeing what's being reflected because that's what's leaving you. There are some sad stories of people that like set up their plants. They're like going away for the weekend or something, or they've got plants inside. They're like, I'm going to buy a green light for my plants so that they can get all the light that they need, and I'm going to set it on a timer, and then they'll be all perfectly happy when I get home, which is not the case because the green light, all of it reflects off of the plants, and then they're basically just sitting in the dark, but you're also wasting electricity, so it's kind of like, it double sucks. So grow lights are usually red, or they've got like a specific wavelength that's tuned for chlorophyll. All right, laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So we're given 515 nanometers, and this is our wavelength. Wavelength has this lambda symbol. And our equation is nu equals c, the speed of light, over lambda. Lambda also the half-life symbol, the video game. And c, my brain just thinking, C spot run, run spot run. 3.00 times 10 to the 8 meters per second. Wicked fast. So to calculate the frequency of the light, we should probably convert this 515 nanometers into meters, since C has units of meters per second. Nano equals 10 to the minus 9. So we can convert this into not scientific notation, but like close enough that we can put it in our calculator. So this is 515 times 10 to the minus 9 meters. Just substitute 10 to the minus 9 in for the nano, and boom, it's in meters. And then we've got everything we need to put in our calculator. So this green light that's at the rock concert, let's find out what the frequency is. 3 times 10 to the 8 meters per second over the wavelength. (515) times 10 to the minus 9 meters. The meters cancel. We'll be left with inverse seconds, which is the same as hertz. 3E8 divided by 515, E negative 9. And the value is 5.825 dot 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 times 10 to the 14. We'll round that. 5.83 times 10 to the 14, and change the units to hertz because we can. Questions? So the number of waves of light is that many waves per second. So that's a whole lot of up and down passing through one point. All right, so visible light, the light that we can see, the light that's pretty, comprises only a small fraction of the entirety of the electromagnetic spectrum. So light is electromagnetic, and it's on a spectrum ranging from really high energy, really short waves to really low energy, really long waves. And light is just a part of that spectrum. Shorter wavelength or higher frequency light is going to have higher energy. Gamma rays, which we'll talk about maybe this semester, I don't remember if it's in Chem 1 or if it's in Chem 1, but you'll talk about when you get to nuclear chemistry. Gamma rays have the highest energy. Radio waves, like the ones and twos, AM, FM, 5G, all that stuff, those are all the lowest energy. Really high energy electromagnetic radiation can damage biological molecules, things we would generalize as ionizing radiation. Gamma rays is one of those. There's actually a lot of gamma rays out and about in the universe, but because of our atmosphere and magnetosphere, we're protected from the vast majority of that from space. If you go into space, then you need your own shielding for gamma rays. So here's a look at the spectrum. And we've got frequency, our value nu in hertz up here. We've got values ranging from 10 to the 24 down to 10 to the 4. Those aren't important numbers, just showing you that over on the right side, we've got really high frequency. This is also our high energy side. On the left side, we've got low frequency, relatively. 10 to the 4 is low frequency. And our wavelengths can be up to 10 to the 5 meters. So like FM, you can measure, like you can visually like draw out the length of the waves. They're relatively long, and some of them get really, really long. And we've got a tiny little smidgen of visible light in there. So our highest energy radiation is gamma rays. Below that, we've got X-rays, like the ones that you get hopefully if you're going to the dentist, or if you break a bone, you probably get an X-ray. Those are also high energy, and they're bad for you if you get a lot of them. If you go and get scanned once or twice a year, it's not a big deal. But if you're an X-ray tech and you're in the room when they're doing the X-rays, that's bad for you. It increases your risk of cancer. You've also got ultraviolet light. This also can give you cancer, but more likely, it's giving you sunburn. It's more energy than violet light. That's the ultra part. It's also right next to the violet light. So notice how we've got UV light, and then right next to UV light is violet light. Any guesses? Violet light, high energy, low energy for visible spectrum? High energy, it's right next to ultraviolet light. Right next to UV, sunburn, cancer. On the other side of the visible spectrum, we've got infrared light, which is just like heat light, which is right next to red light. Infra meaning below. So below red light, we've got infrared light. And some like heat lamps use infrared light, or like they say that they're infrared heaters. So they just like blast you with heat waves. And then microwaves, which are used for microwaving food and other things. And then the last thing that I'm going to show you before we stop for today is a helpful tip/trick for remembering the order of light with respect to wavelength. So the ultraviolet, the UV violet light being high energy, red light being low energy. I think that's nice. Energy is directly related to frequency, high frequency, high energy. On a rainbow, what's the outside color? Red. Outside color of a rainbow is red. And then I'm missing some colors, but we'll draw out most of the rest of it. If we were to take this rainbow and straighten out all the parts of the light, all the different like beams of light, the bands of color, which one would be the longest? The red light, because it's on the outside track. So red's the longest. Which one would be the shortest? Violet or purple? Violet is shortest, it's that inside track. Conveniently, this also corresponds to their wavelength. So red light is the longest, it's the outside band of the rainbow, and our shortest wavelength is violet, which is the inside band of the rainbow, and everything between is in the color order that you would expect it to be in for a rainbow, which I think is just very cool. Any questions before we wrap up? Stop. Cool, then that'll do it for today.